This is Mr. Alexander, and I want to talk to you about rates of change and finding local maximums and minimums. The first thing I want to talk about is rates of change. To put it simply, when the function is sloping upwards, then it has a positive gradient, and when it's sloping downwards, it has a negative gradient. At these flat spots here, here, and here, that is a gradient of 0. So when I ask you to write down the values where the gradient equals 0, we would start with this one right here, x equals negative 1.5. The next one right here appears to be at negative 0.25. And then this last one's kind of just past 0.5. Let's call it an even 0.625 because it's about halfway between 0.5 and 0.75. Using those 3 points, I can identify where the gradient is positive and where it is negative. So there's 2 spots where it's positive. From here to here, negative 1.5 less than x less than negative 0.25. And also from here to here, x is greater than 0.625. That'd be the 2 intervals where it's positive. Now the 2 intervals where it's negative, here to here, here to here, that'd be x is less than negative 1.5, and also when x is between the negative 0.25 and 0.625. So you can approximate these x values sometimes because it's not always perfect, but whatever numbers you use here, you better use here in the intervals as well. That's the less important part of the lesson. The more important part of the lesson is locating local maximums and minimums. So I want to show you a few of those problems next. I'm just going to pick one of these, A, B, C, or D, and I'm going to use that as an example. Probably the most imposing one, because it's not a pure function right now, is this one. So I'll go ahead and do C. First rule my Calculus 2 teacher told me in college was whenever you can do algebra, you should do algebra. So I've got this x 9 plus 3x minus x squared, and I just want to simplify that as much as possible. I'm going to change that to 9x plus 3x squared minus 3x to the, minus x cubed. So that's my function. To determine the coordinates of any turning points are simply where the slope turns from negative to positive, call them local maximums and minimums, on the given curves for each to decide if it's maximum or minimum. The first step is to find the gradient function, which is dy dx. This is going to be 9 plus 6x minus 3x squared. The next step on this is the local maximums and minimums always occur when the gradient equals 0. So I'm going to replace this gradient with 0. 9 plus 6x minus 3x squared. Now, that's a quadratic set equal to 0, and you know lots of ways to solve a quadratic. You could use the quadratic formula. You could use factoring. There's lots of things you can do, but my preferred method in IB Math Studies is always to graph it and see where they intersect. So I'm putting the left-hand side 0 into y1, and I'm putting the right-hand side 9 plus 6x minus 3x squared into y2, and I'm going to hit that graph button. And I can see that this thing crosses the x-axis twice, which means I'm going to have 2 turning points, probably one local max and one local min. To figure out the coordinates of those points, I'm going to do second trace 5. I'm going to find the intersection of those two. And the first one occurs at x equals 1. So I'm going to write that down. And the second one occurs at second trace 5. Scroll over a bit. Enter, enter. X equals 3. Like that. So now, I've got the x coordinates, but I don't have the y that's associated with that. So I always like to write at x equals -1, y equals something, and at x equals 3, y equals something else. Now I always use the calculator cheat for this as well. The way I do that is I'm typing the original equation into y1. That's going to be 9x plus 3x squared minus x cubed. And you can just go to the table. At x equals 3, y equals 27. Oops, wrote that in the wrong spot. And then at x equals -1, y equals -5. So the question now is, are these two coordinates, -1, -5, and 3, 27, are they local mins or local maxes? And I'm just going to hit the graph button here, and I'm going to hopefully be able to make that determination. So if I was to draw a rough sketch of this thing, and it can be really rough. There's my x, there's my y. Let's say this thing kind of looks like this. So at -1, -5, that appears to be a local minimum. So I'm going to write that. Now I wouldn't say that this thing is an absolute minimum, because the absolute minimum occurs at the very bottom, the very lowest y value on this graph. And this thing's going down forever. There is no absolute minimum. And if there is, it's at -infinity. What about 3, 27? That appears to be a local maximum. And it's not going to be an absolute maximum because, as you can see, this in the left direction, it goes up forever. So there is no absolute minimum, there is no absolute maximum, but we do have a local min and a local max. And that's the process. So in summary, just find the gradient function, set it equal to 0, solve for x, and then figure out what those x, y coordinates are. Are they local mins, local max? The easiest way to do that is simply graph them. All right, I've got some time to show you some IB problems, which I'd like to do now. And in particular, I'd like to show you this problem. Consider the graph of the function y, or f of x equals x cubed plus 2x squared minus 5. I believe this was on the IB exam last year. Label the local maximum as A on the graph. Well, that's easy. Right there. There's A. And label the local minimum as B on the graph. Okay, there it is, right there. Write down the interval where the gradient function is less than 0. Meaning, where is it negative? Where is the gradient negative? Well, the gradient is negative in the only place where this function is decreasing. It's right here. Now, I could write that interval if I knew what these two coordinates are. I'm a smart person, and I happen to know what the coordinates of this one are, because the function is x cubed plus 2x squared minus 5. That's the y-intercept, so that's going to be 0, -5. I know that. What's that value of A, though? I'm going to show you another trick. What we could do, based on what I just showed you, is we could take the gradient function, find the gradient function for this and set it equal to 0, solve for x. That's a long way. In this case, since I already know it's a local maximum, what I'm going to recommend we do is we type in the function, do x cubed plus 2x squared minus 5, hit that graph button. There's the maximum right there. Let me just change my window a little bit so you can see it better. There's the maximum. We can actually have the calculator tell us the exact coordinates of that maximum by doing second trace 4. And then if we get on the left of it, hit enter, get on the right of it, hit enter, the calculator is just going to tell us what those coordinates are. -1.33333333, comma, 3.81 to 3 sig figs. So I'm going to write that down. -1.33, comma, -3.81. Now I don't actually need the y value in either case. I just need the x value, because when I'm writing the interval, we usually write an interval in terms of x. So the interval where the gradient is negative happens to be between negative 1.33 and 0. Now I didn't write less than or equal to because at those 2 points the gradient is 0. So don't write or equal to, just when you're writing an interval, make sure it's just less than. That was an IB problem from last year. I have enough time to show you another IB problem. And so I'm thinking between the two of these, this one's probably the better one to go over. And this will be the last one we do. Consider the function f of x equals ax cubed minus 3x plus 5, where a does not equal 0. Find f prime of x, which is just the first derivative. Well, f prime of x is going to be 3 times a x squared minus 3. Easy. The 5 disappears, obviously. The next question says, write down the value of f prime of 0. Well, let's just plug it into 0 into the gradient function. That's 3 times a times 0 squared minus 3. Well, 0 squared is 0 times anything is still 0, minus 3 is negative 3. Baby stuff, baby stuff. But let's do some calculus now. The function has a local maximum at x equals negative 2. Calculate the value of a. We can do that by remembering that the local maximum occurs where the gradient equals 0. You're saying to yourself, okay, but now I've got two variables. I've got an a, I've got an x. And I can't solve an equation with two variables unless I have two equations. But we actually have another piece of information. They tell us x equals negative 2. So I'm going to plug that negative 2 in there as well. Negative 2 squared is 4. 4 times 3 is 12. I've got 0 equals 12a minus 3. I'm trying to solve for a. You add the 3, divide by 12. 3 over 12 is just 1 over 4. And I'm supposed to use that information to find the coordinates of the local maximum. Well, I know that the first coordinate's a negative 2. They told me that. Or how am I going to get that y coordinate? I'm going to use this a, plug it back into the original equation, and I'll just use the calculator to help me out. So I'm going to type in here, 1/4 is just 0.25, x to the third power, minus 3x plus 5. And I'm just going to take a look at what's going on at x equals negative 2. At negative 2, it's the value of y is 9. Now I'm just going to graph this thing to make sure I'm not crazy. Indeed, there is a local maximum at x equals negative 2, so I'm feeling pretty good about that. So is a local maximum. And hopefully you agree that's a local, not an absolute maximum, because you can see this cubic function is going to keep going on up forever. All right, that's all I have time for now. Thanks for watching. Next time we'll be talking about optimizing these functions, so that'll be fun. Thanks for watching.